All right, today we're going to look at RC circuits, which, as the name implies, are circuits containing not just a capacitance, but also a resistance. So we'll start by looking at the function of the capacitors in short and long time scenarios, and then we'll go to solving some differential equations to go through the transient state, or the in-betweens. So, when we think about what a capacitor is, we know that they store charge. And without a resistance, we've been assuming this process occurs instantaneously, where as soon as you connect a capacitor to a battery, it establishes the correct voltage across it, and there's no sort of charging process, it's just instant. Now, of course, with a resistance, it's going to take time because you don't have infinite current, so you can't transfer all the charge you need at once. You have to sort of wait. And we'll cover that sort of transient state later, but first we're going to look at the short and long time special cases. So we do know what the circuit should look like at the short and long time scenario after the capacitor begins to charge, and that shouldn't require any calculus. So at short times, our capacitor isn't charged. So that means there's no potential difference across the capacitor, meaning all of the potential difference must be across the resistor. So as such, we can pretend that the capacitor doesn't exist at a short time and it's just a wire. And conversely, at long times, all of your circuit's potential difference is across the capacitor because you've fully charged it. And you know that because if there was still current through the resistor, then that would be charging the capacitor. And if there was current through that resistor, there'd be a potential difference across it. So it's not the entirety of the battery's voltage. So that's how we can reason that at short times, all of the battery voltage drop has to be across the resistor. And at long times, all of the battery's voltage drop has to be across the capacitor. And this is, of course, just a simple series circuit. You can get hybrid cases of these with more complicated circuits, but a short time capacitor behaves like a wire, meaning no resistance, and a long time capacitor behaves like a gap, or infinity resistance. So another thing to note is actually during this charging process, what's happening? Well, this is a gap, and usually it's a dielectric material or an insulator. So we don't just have charges that just jump across the gap. What we have instead is you can almost think about if this plate becomes positive and this plate becomes negative, electrons are going to get pulled from the positive plate and sent to the negative plate. So nothing crosses the gap. I thought that's an important note to say here because really we talk about current flowing like around the circuit and we talk about current flowing through the capacitor like it's a wire, but just note that it's not truly flowing through the capacitor gap. It's really the electrons are getting pulled from this end to this end, which in turn looks like a conventional current in the way we expect. But again, that's just our model, and this is a really good model. So one thing to note is this short times case can actually cause some interesting results because if the capacitor behaves like a wire, this can cause a short circuit in situations where you have other resistances in parallel. So if I had a bunch of resistors over here, they wouldn't even receive current at all in short times. So just keep a note of that because a short circuit, if there's ever a zero resistance path, all current will flow down the zero resistance path. If it's not zero resistance, of course, it'll partially split. But just realize if you have a free path back to the battery, it doesn't go through the resistor at all. The current, that is. So let's do some modeling here. At time t equals 0, we close a switch in a simple RC circuit for the first time. And we're going to model what the effective circuit looks like in the short and long times. Okay, so what about short times? Well, at short times, we say a capacitor is modeled as a wire because there's no potential difference across it. So when we say draw the simplified circuit, we mean replace the capacitor with the object that models that limiting behavior. So I am literally just replacing my capacitor with a wire. And what do we notice? Well, if we try to color code our circuit here, with red being our high potential and 0 being our low or ground, when we reach the capacitor, we see that this is a wire, and there's no potential difference across an ideal wire. So what we see here is that all of our potential difference is dropped across our resistor. So we actually know that I is just going to be our battery voltage divided by the equivalent resistance, which is just epsilon over R. So at short times, it behaves like a circuit without a capacitor in it at all. So what about long times? Well, after a long time, this capacitor behaves like a gap or a hole in the wire. So I'm going to start off the same way. We got our battery, we have our resistance, and then we have our capacitor. So what is our capacitor? We're saying it is a gap in the wire. I always like to put X's to show my gap, just so I'm really clear that I meant for there to be a hole there and I didn't just draw a bad circuit diagram. So if we draw our potential diagram here and start to do this, we see that my blue reaches this gap right here. And well, this is a gap, so there's no current flow. And if there's no current flow through a resistor, then the potential difference across it can't change, or there is no potential difference across it, I should say. So because this is an incomplete circuit, we said you only get a color change or potential drop across a resistor if you have current flow. And if there is a literal hole in your circuit, you can't get current flow, so there is no potential drop. So what does this say? Well, this says that there's no current, so all of your potential difference is actually across the capacitor. So this would be the charged state, right? Because as your capacitor gets more and more and more charged, the potential difference across it is going to increase until it eventually is the entirety of the battery voltage. So we see that it's an entire red to blue. So of course, there's all these intermediate states where it's a mix of these two, where it's not all dropped across the resistor, nor is it entirely dropped across the capacitor. But these limiting cases are easiest to analyze. All right, so let's determine everything. All right, the resistance at short times. Well, in short times, we see it is just a simple Ohm's law circuit. It's just a EMF epsilon in series with a resistance R. So you feel the full voltage drop of the battery. And then for current, we just use Ohm's law. And then for power, you can pick your favorite power formula. There's 3 of them. But here we actually just have the 2 quantities we'd need for the definition of power, I delta V. So if I multiply my I and delta V together, we see I just pick up an extra factor of the battery EMF. Now you could have also done this by I squared R or delta V squared over R. I think this is very clearly delta V squared over R, right? Now what's going on in the capacitance? Well, I have no potential difference. I think that's the easiest one to see, right? It's blue all the way across. So there's no voltage drop. Well, if there's no voltage drop, there's no charge. And if there's no charge stored, there's no energy stored in the E field. So why do we know that? Well, we know that Q is C delta V for charge, and then pick your favorite energy storage formula. I'm going to mirror the power calculation to just show the definition of that. And remember, we get a 1/2 for the capacitor energy formula because it doesn't cost you anything to move your first bundle of charge, but it costs dq delta V to move your last bundle, so we get this sort of average idea with the 1/2. All right, what about long times? You can probably guess that it's going to sort of flip-flop. And it is, right? Because I see that there is no voltage drop across my resistor. It is red to red. And why is that? Well, there's no current through the resistor. There's no current because the loop is not closed. So if there's not a closed loop, you don't get current. Now this means the capacitor has all of the voltage drop. So then we can find our charge stored by Q equals CV, and we can find our energy stored by 1/2 Q delta V. So Q is just going to be CV, which is the capacitance times epsilon. And then energy stored is 1/2 of these two multiplied together. And we get 1/2 times C times epsilon squared. And oh, look at that. That looks just like one of our other capacitance energy formulas, right? Because we said U could be 1/2 Q delta V is the definition, which is 1/2 C delta V squared if you substitute away for Q. Or that's equal to 1/2 times Q squared over C if you choose to substitute away delta V. So you can use any of these depending on which of the two of the three capacitance quantities you know. All right, so that's not really interesting. This is just our base case. Now, what is more interesting is this scenario, where it's not a simple circuit because we have resistors in different places. And it's also not a series and it's not a parallel. We don't really have a name for this because the resistor isn't in series with the other resistor, nor is it in parallel. It's sort of in parallel with this capacitor. So we have to do our short and long-term analysis. All right, this is definitely going to stay the same. Draw color-coded potential diagrams for the simplified circuit in each of the limiting cases, short and long times. So regardless of how complicated your circuit is, we know that C is equal to a wire in short times, and C is equal to a gap at long times. So I'm going to draw my sketch of everything but the capacitor. So you're 20 volts. You are 5 ohms. Again, I'm not drawing the capacitance branch yet. And then there's also a 15 ohm on the side. Okay, so before I start coloring it, I'm just going to save myself some work in a minute here. Just gonna copy, paste. Okay, saves us both some time if I do that. All right, short time after the switch is closed. What does that mean? Well, C is a wire. So if C is a wire, that means you can't drop any potential across it. So let's draw our picture. Positive, that's my high potential. I hit a resistor, so I stop. Then for my low potential, my 0 point, I explore all the possible paths. So I reach a boundary this way. So again, we say the potential explores all the paths until it's encountered every single roadblock. There's a roadblock, explores all paths. And notice we get something interesting here. I've actually colored the entire, right half of my circuit blue. Why did that happen? Well, this is a short circuit because we have 0 resistance in parallel with 15 ohms. And if I have a resistance-free path, all of the current will actually go down that resistance-free path. So what does this mean? This means the 15 ohm is shorted. So that actually means REQ, it's not 20. It's actually just 5 ohms. Because that 15 ohm resistor gets ignored. It must be. Both sides of it are at the same potential. Because this current sees a free path back to the battery. And actually, if we're interested in what that is, the total current is just going to be the EMF divided by REQ, which is 4 amps. And I know we'll need it later, so I did it. So if you ever have a case where with this short time capacitor being a wire, you will often have to ignore a huge section of your circuit at that time. So actually, let's solve everything with that first, because that's what it's going to ask us. All right, so short times. Our 5 ohm resistor is the only thing receiving current right now, and we see my entire red to blue potential difference is across the 5 ohm. So all 20 volts are across U. So what's the current through that? Well, the current through that is going to be 4 amps, because Ohm's law says current is delta V over R. And then for my power, I'll pick my favorite of the expressions, or just the easiest one here, I delta V, and that gets 80. And the units, again, power is energy per second, so it's joules per second, which is 8 watts. Now, this is the tricky one. What's going on with 15 ohms? Absolutely nothing. It is shorted. So since it is shorted, that means that we are just going to ignore that. So zeros all across the board. Okay, what's going on with the capacitor? Absolutely nothing. There's no potential difference across it, so there's no charge and no stored energy in the E field. Okay, long time. Well, long time, it says C equals gap. So again, I just want to intentionally show that I'm drawing a gap here. And now we'll try our potential color coding again, and we get something very different. So red hits the 5 ohm resistor, no other exploring can happen there. Then my blue explores. It hits the same 15 ohm resistor as before. And then last time it got to explore all the way up this short circuit, but it can't anymore because there's a hole. So the blue stops there. So notice I have red and blue, and this is a complete loop. So there's going to be some potential change across here. So this actually means I need a third intermediate potential color for this. So with there being a gap essentially means you can just ignore whatever's going on in that gap. So that means I'm essentially crossing off this, and this just looks like a series circuit. So REQ is equal to 5 plus 15, which is equal to 20 ohms. So this means my current is the same 20 volts divided by 20 ohms, which is exactly 1 amp. So again, the current would really love it if it had a zero resistance path to go through, but it doesn't. So the current would really like if this was a wire, but it's not, so it's forced to go through the resistive 15 ohm path. All right, so these two are in series. So resistors in series, of course, receive the same current. They're in a loop together. No junction rule. Things can happen there. So to find voltage drop, we use good old Ohm's law. Delta V is IR. Really easy because I is 1. So you drop 5 volts and you drop 15. So this means the power dissipated is also really easy because P is I delta V. So I just multiply those two together and I get 5 watts and 15 watts. All right. So also check the loop rule works, right? The loop rule definitely works. And we're going to label this because this helps us later. So loop rule says you got to drop all the battery voltage by the time you make it back around. And we just solved for these delta V's. And we see that. So what's going on with the capacitor? So the most common mistake with the capacitor is saying that at long times, the capacitor always drops the battery voltage. And that should be clear that that's not actually happening if we look at our circuit diagram. Because if we look at our circuit diagram, we see that red to blue is 20 volts. And this is not red to blue, this is yellow to blue. So remember that objects in parallel receive the same voltage drop because they make a Kirchhoff loop. So if I start at the battery, I have 20 volts to drop. I've dropped 5 over the first resistor, and I've dropped the remaining number across this capacitor. So, of course, this has to also be 15 volts because it has to satisfy the loop rule, or you could just say objects wired in parallel receive the same voltage drop. So that's actually worth an explicit note that this is in parallel with the 15 ohm. So it gets the same delta V. So you might have to be creative in figuring out what is in parallel with what. Like maybe I have a series of resistors in parallel with the capacitor that add up, but same idea. All right, so what's the charge and energy? Well, charge, Q equals CV, and then U equals 1/2 Q delta V. All right, charge stored. Well, we got to multiply these two numbers together, 30 and 15. Well, that's 150 times 3, so that's 450 in units of microcoulombs. And then what about the energy stored? Well, it's 1/2 Q times delta V. So it's half of 450 times 15. And using the power of I did this before, it is hopefully 3,375 microjoules. Now, at this point, you probably might just want to use like regular numbers instead of micro, because this would be 3,000 times 10 to the minus 6, so you're in like the milli territory now. But whatever. It's more about the process. So we see that unlike the simple case, you actually get current flow in the circuit and a charged capacitor, both at the same time, when you're in steady state, when you have situations like this. All right, now we have a similar situation. The switch in the circuit below has been closed for a long time. We're actually going to define what long time means in a few problems here, but realize that long time means enough that you can say the capacitor is fully charged. We'll define a time scale for these circuits shortly, but just realize that this means that it's closed for a long time, so we can model C as a gap. What does it want? It wants the energy stored by the capacitor once the circuit reaches steady state conditions. Okay, steady state conditions, and we want energy stored. So there's three ways of finding energy stored by a capacitor. So we have U equals 1/2 Q delta V, which is equal to 1/2 C delta V squared, which is equal to 1/2 Q squared over C. Now, the most common incorrect answer would probably just be saying, well, I see a capacitance C and a voltage of epsilon, so it's 1/2 C epsilon. Now, of course, that makes the same mistake as in the last problem, where we think that the capacitor must hold the entire battery potential difference, but we know we're going to get that situation again, where there's going to be some voltage dropped in other places, and we have to be a bit clever. So, it does seem like this 1/2 C delta V should be our goal, because we know nothing about Q, and delta V is usually easier to find for circuits. So all we got to do is find the voltage drop across the capacitor, and we're good. So let's do that. Yeah, we have a good amount of space. We can do this here. All right. So to begin, we'll start by drawing our simplified circuit. So at long times, you are a gap. So we know that this is a gap. So let's redraw. So we got a battery. We have a 2R resistance. We have a capacitance that is a hole. And then on the side, we have an R and a 2R. All right, so let's do it with color coding our potential here. All right, high potential, no other paths. Low potential, no other paths. So then I bring out my first intermediate potential, and I'm actually still not done because there's still this area. So I actually need a fourth color here. So I'll do yellow for this. So we actually have 4 unique potential values in this circuit. But realize that, again, this gap can basically be ignored because no current flows through it. So essentially what I have is just a nice little series circuit. So REQ for this circuit is a 2R, an R, and a 2R in series, which is 5R. So that means that my current through the entire circuit is just going to be EMF, the EMF over 5R, which is 1/5 times epsilon over R. All right. So why is that helpful? Well, that's helpful because now we can calculate the voltage drop across these different circuit elements. Because we know that delta V across the first 2R is just going to be I times R, which is 2R in this case. So we get all the symbols cancel except for epsilon, and then we get a 2/5. So this is 2/5 epsilon. Then delta V across the resistance R by similar logic is going to be 1/5 epsilon. and then delta V across the second 2R is going to be 2/5 epsilon, right? They all receive the same current, so I'm just plugging in my delta V, my I for delta V. Why is that helpful? Well, of course, we want the voltage across the capacitor, which we didn't include at all through this. So we said U were 2/5 epsilon, U were 1/5 epsilon, and U were 2/5 epsilon. Let's see if we can scoot this up. Yeah, we can. Nice. Okay, so why is this gonna unlock our capacitor? Well, I'm just gonna rewrite this while I talk. So we said this was 1/5 epsilon. Well, we want the potential difference across this object right here. And notice there's two ways of getting it. So first, it's easy to see by the loop rule that if I dropped 2/5 of the battery across the first resistor, I have to drop the remaining 3/5 across this one because it makes a closed loop. I can go from the battery to the 2R to the capacitor and back. So this closed loop right here has to work out, so it's 3/5. Solution 2 says my capacitor color change is orange to blue. So if I go from orange to blue, I can also get from orange to blue by going through this resistor, which is 1/5 epsilon, and this resistor, which drops 2/5 epsilon. So the drop from orange to blue must be 1/5 plus 2/5 equals 3/5 times the battery voltage. And yet a third way of visualizing it is saying that orange to blue is really in parallel with the 2R and 3R together. So a couple ways you could have reached the 3/5 epsilon. I personally would have looked at it the first way. So I actually would have stopped after calculating the 2/5 epsilon across the 2R and said, well, if I drop 2/5 across that one, I must have dropped 3/5 across the capacitor because it makes a loop. So we're still not done because now we can just plug in and we can say that U is equal to 1/2 times C times delta V squared, which is 1/2 times C times 3/5 epsilon quantity squared, which is 1/2 times C times 9/25 times epsilon squared, which is half of 25 is 50. So we get 9/50ths C epsilon squared. So that's not easy. A lot of steps going on there. So realize this is not just the battery voltage, right? You have to do all this to figure out exactly what proportion it is. Now, if you're trying for doing it big brain, like galaxy brain way of doing it would be seeing that the capacitance is in parallel with 3 R's of resistance. And 3R is 3/5 of REQ. So I actually know 3/5 of the battery must be dropped across it. That's how you could theoretically do it in your head without writing anything. So that's all we can really talk about for short and long times. And now this is what makes it the C topic, is we're talking about the transient state. So what happens in between short and long times? So there's actually a very well-known function that shows how this function behaves for charge or voltage or current. Any of these follow one of the following forms. So if your circuit quantity is building up, it follows this parent graph, which I've been calling exponential approach. Some students in my class have been calling this exponential zombie for a reason I cannot possibly explain. But I call this exponential approach, where it's definitely a decay, but it's the rate that's decaying. So the charge on the capacitor starts at 0, ends at some maximum Q. And how does it get there? Well, it's actually this decreasing slope curve. And what characterizes the rate that it climbs is this quantity called tau, the time constant of the circuit. And the lower values of tau means that it charges faster. So the bigger the time constant, the slower your capacitor charges. This is close to the concept of half-life from chemistry, where it dictates how long it takes for your isotope to halfway decay. except the quantity in this circuit is not 1/2, it's E. So this coordinate on the graph for our time constant isn't 50%, it's actually 63%. And that's because if we work it out, so we're really looking at e to the negative t over tau. So if t equals tau, then we get e to the -1 because we're dividing the same thing, right? Tau divided by negative tau is -1, and e to the -1 is roughly 0.37. So 37% is kind of the main value we're looking at for time constant. And in this case, after one time constant, it's 63% of the way there because we're doing that 1 minus idea. So after one time constant, a capacitor only has 37% left to go, basically. And if your capacitor is discharging, that means the same thing, where it's 37% above zero. This isn't super important, but it isn't like important to understand the scale of things. That this tau is kind of like a half-life, but it's more like a 37% life. So for discharging, it looks basically the same, except you don't have the 1 minus. So this is just a pure decay. And this one, it's actually easier to look at what tau means. So after every 1 half-life, your circuit quantity gets multiplied by 37%. So after 3 taus, or 3 time constants, you would have 0.37 cubed of your original charge. So we can see it keeps decaying exponentially like that. And it turns out there's actually a really simple way to find the time constant of an RC circuit. And remarkably, you can actually get a time unit just by multiplying resistance and capacitance together. Now, these are the equivalent resistance and capacitance values, so you might have to do some series and parallel combining of each. But yeah, that's kind of your value. So it should actually make sense, because if resistance is high, you're going to get less current. And if you get less current, you're transferring charge to the capacitor at a lower rate, so it's not going to charge as quickly. And if capacitance is large, well, you need a lot more charge to get the same potential difference, because capacitance says how much charge does it take to get a certain potential difference. So it makes sense that both of these are have a positive relationship with the time constant. Now, if you don't believe me that this is actually a time unit, we can work it out. It's not terrible. So we said that R is ohms. Okay, that's not helpful. What is an ohm? Well, remember that we have delta V equals IR, so that means R is delta V over I. So an ohm is a volt divided by a coulomb, and I'm writing coulomb like that just to not confuse you with the letter C. Coulomb per second, sorry. Because an amp is a coulomb per second. And then what is capacitance? Well, capacitance is a farad, all right? Also not helpful. What's a farad? Well, remember that capacitance is defined as charge per volt. So this means that this is a coulomb per volt. So this means RC is equal to volt times second over coulomb times coulomb per volt. Goodbye coulombs, goodbye volts. And look at that, we do actually get seconds. So there's a nifty little unit, a unit check for you there. I know it's hard to imagine because we usually don't use base units. We define things like ohms and farads and amps, but it works out. All right, so here we have a discharging capacitor. So at time t equals 0, we have this fully charged capacitor, and at t equals 0, it releases its charge. So again, what does releases its charge actually means? What it really means is electrons are going to leave the negative plate and flow back, but of course we can just model this as a battery with conventional current. All right, first, determine the time constant of the circuit. Well, Of course, the time constant of the circuit, we said tau is equal to Req times Ceq. Okay. So there's no capacitors to combine here. There's just a single capacitor. So that equivalent capacitance is just C. So I just got to find Req for this circuit. So what is Req? Well, I have 6 and 3 over here, and those are in parallel. So 1/6 plus 1/3 to the negative 1 is that resistance. And here's a quick trick for doing parallel in your head if possible. If you're combining two, and again, this is only two resistors in parallel, you can always find the equivalent resistance by doing the product divided by the sum. So I actually know that this in my head is going to be 18 product over 9 sum, which is 2. And I actually didn't have to do that. I know this well enough. I always like to use 6 and 3 because 6 and 3 works out very nicely. So then notice I just have a 2 in series with another 2 because 6 and 3 make 2. So 2 plus 2, it's 4. So this is 4R times C. So my time constant is 4RC. Determine an expression for the charge on the positive plate of the capacitor as a function of time. So in this situation, there are exactly two parent functions you have to learn to plug into. We have exponential decay, where it's some maximum value decreasing to 0, or it's exponential approach, where it's some value increasing from 0 to an asymptote. And here, we're starting with a discharging capacitor. It's charged, and then it's releasing its charge. So it follows this form. So I'm going to plug into this parent function. Now, we'll prove these are the models later. That's what requires calculus. So Q is equal to Q max times e to the negative t over tau is our parent function for decay. And I probably told you what Q is. Yep, I did. It holds initial charge Q0 on its positive plate. So my maximum charge is Q0, and my time constant is 4RC. Derive an expression for the time required for the capacitor to reach 1/4 of its initial charge. So we can first kind of work out kind of where this should be. So we know that after 1 tau, or 1 time constant, I'm at 37%. So after 2 time constants, I'm at 37% of 37%. And again, that's roughly divided by 3. So I would expect it to be somewhere, it's definitely somewhere between 1 and 2 time constants if I were just to guess. So how do we get that explicitly? Well, we have an expression for Q. So we want to see how long does it take until Q is equal to 1/4 of your original. And actually the physics is done. This is actually a pre-calculus question now. So we just want to see 1/4 Q0 is equal to Q0 e to the negative t over 4RC. It's actually independent of Q0, which you start to get a feel for with these exponential problems, because it depends on themselves, just like the lone question. So we get 1/4 is equal to e to the negative t over 4RC. Okay. Now we have to get rid of, or we're trying to solve for this t in the exponent. So if we're doing that, that means that we need to take the natural log of both sides to remove that. So we can write natural log of 1/4 is equal to natural log of e to the negative t over 4RC. And you can only cancel e and ln if they touch. So here they touch, so they cancel. So we get ln of 1/4 is equal to negative t over 4RC. So t would be equal to negative 4RC ln of 1/4. And this seems kind of weird because we have a negative time, but it's actually not negative because ln of 1/4, this is asking what do I have to raise e to? to get to a quarter, and that's a negative power. So we can actually use a nifty log property that says we can bring numbers inside the log as powers. So this uses this rule that, remember that, well, we'll write the answer first, then I'll justify it. We can write this as 4RC ln 4. So why can we do that? Well, there's a log property that we're just saying that negative ln of 1/4 is the same thing as ln of 1/4 to the -1. And again, 1/4 to the -1 is flip the fraction 4. That uses that power rule for logs. So this answer does make sense, because what is ln of 4? Well, ln of 4, that's what number do I have to raise e, which is 2.7. What do I have to raise 2.7 to get to 4? Well, it's bigger than 1 and less than 2. So as expected, it's between 1 and 2 time constants. Because 4RC is the time constant. All right, this is a much more typical question, is ranking charge time. So we see we have most of the combinations of resistors and capacitors that you can come up with if you have 2 of each, 1 or 2 of each. We're going to rank the time required for each capacitor to reach 50% of its steady state voltage upon being connected to the battery. So this is basically the half-life. We're asking for the half-life. And it makes sense if we're talking about charging time. It isn't the time constant, but it's proportional to it. It's really off by like a factor of log 2. So we're looking at charge time. So that's going to be proportional to tau, which is equal to RC. So we're just trying to find RC for each of these circuits, and we're going to rank them. And we'll do all our work on the front. All right, circuit 1. Well, remember our combining rules. Resistors add in series, capacitors add in parallel, and then the other is, of course, the reciprocal. So this is 2R, and this is 1 over C plus 1 over C to the -1, which is C over 2. Because we also said if you combine identical things using the reciprocal rule, you just get division. So circuit 1 is just going to be 2R times C over 2. So your tau is actually just RC, because of canceling effects. Circuit 2. Well, we have 2 resistors in parallel, so that's just going to end up as division when we add those. 1 over 1 plus 1 over 1 to the -1 is 2. And you are just C, because there's no addition. So we get RC is just 1/2 times 1, so 1/2 RC. Circuit 3, you are just R. And remember, parallel capacitors add. So because parallel capacitance increases with plate area, and this is a bigger plate area, so it should be a bigger capacitance than originally. So this is 2C, because it's C plus C. So our time constant RC is R times 2C, which is 2RC. Now, what about circuit 4? You get halved, you get added. So that makes you just RC once again. So we can just quickly zoom back out and kind of see what we have here. So both things in series canceled out, right? Because series adds for resistors, but reciprocals for capacitors. Adding both in parallel also canceled the effects, because parallel decreases resistance, but it increases capacitance. And then when we mixed them, that's where we got our different time constants. So we see that circuit 2 has the lowest time constant, so that's going to charge the quickest. Then 1 and 4 tie. And then 3 has the longest time constant. And again, conceptually, it should make sense that 2 takes the least time to charge, because we have only a single capacitance by itself, but it has the least resistance, so that charge is getting pumped out of the battery the quickest to charge that capacitor. So we just rank REQ times CEQ for each circuit, which we did on the front, so I'm not going to bother rewriting it. I don't find that particularly worth our time. All right, now we have to do it. It is time to solve the differential equation. So where does this magical solution spawn into? Well, where does it spawn from, I guess? The answer is, of course, calculus. If you see E floating around, it's probably calculus. And this looks scary, so we're actually just going to derive this. So all of our differential equations for circuits come from Kirchhoff loop rule, because some voltage drops depend on current, right? That's the resistor, but others depend on the charge itself. So we have an equation that has the charge and a rate of change of the charge. So that creates a differential equation. And if they're dependent on each other in a proportional way, that's kind of why we're going to get E. And this actually works in both cases. I'm going to say please set it up with a battery voltage in both cases, even if there is none, because it saves you a lot of time actually of messing with signs. So even in circuits with no battery, this equation still works. We just have to manually set the battery voltage to 0 after we write our first line. Now, there's a more precise way of getting the discharging equation without having to create a phantom battery that instantly vanishes, but just trust me on this one. All right, let's do the charging case. So what does Kirchhoff's loop rule say? Kirchhoff's loop rule says the sum of all the voltage drops around your circuit has to be 0. So I gain voltage across the battery. That is an increase in potential. I go from low to high. Then I drop some potential across the resistor. Then I drop some potential across the capacitor, and then I've returned home. So again, if we're conceptually color coding this, we're going to assume that the switch is closed. So I think we're actually going to close this switch. So we see that we'll get some potential dropped across the resistor and the others dropped across the capacitor. And together that has to equal the battery voltage. Because this is not long time or short time. This is intermediate. So we are going to get both. All right, what is potential difference across a resistor? Well, potential difference across a resistor is IR by Ohm's law. Now, voltage drop across the capacitor, that's a bit more. That's probably not one we know off the top of our head. So if we start from Q equals C delta V, or the definition of capacitance, we can get delta V is Q over C. So this is a valid loop equation, but it's not a differential equation yet, because we see that we don't have a derivative yet, but we can make one because we have Q and I, and we said current is the rate of charge flow with respect to time. So we can get EMF minus dq dt times R minus Q over C is equal to 0. And that's actually something we could box. Like if you're writing on the exam and it says just write one, don't solve it unless it asks you to. Like you don't have to solve for any of the things. You could just write this. As soon as the derivative shows up, it's valid. But to help motivate it later and do some algebra on this page, I'm actually going to solve this for dq dt. But realize this is acceptable, and I would box this if I were you. All right, so let's try to solve for dq dt. So I could add this term to both sides, and I would get R dq dt is equal to the EMF minus 1 over C times Q. I just moved the Q out in front because it's the function to help distinguish it. And then if I divide everybody by R, I get dq dt is equal to EMF divided by R minus 1 over RC times Q. So now we're probably seeing something interesting. So not only is RC the time constant, it's also the name of the section. And we see that that shows up in our differential equation. This quantity RC is in front of the Q. And not just RC, it's actually negative 1 over RC. All right, let's solve this. So we're going to show 2 ways of doing this. Now, I'm going to show you the by the book way first, but realize the by the book way is like a mess. for this. It is quite annoying. There's lots of algebra. You will mess up if you're not careful. So I'll show you a way that seems like just a total hack, but it's actually valid. And if you have a problem with it, well, that's just differential equations. It's just a bag of tricks. So I'll show you the by the book method first. So we are trying to solve. So the by the book method is we are trying to solve dq dt equals epsilon over r minus 1 over rc times q. So the book method says separate, integrate, and solve. So separate means put everything containing a q on one side and everything not containing a q on the others. That's at least how I choose to do it. So we can't just add this term to both sides, because then if I multiply by the dt, we'd be mixing some things. So I'm going to start by writing dq equals epsilon over r minus 1 over rc times q times dt. So that's clearly not separated. So I can separate by dividing everything in the parentheses on both sides. So I get dq divided by epsilon over r minus 1 over rc times q. And that's going to equal nothing times dt. So that's called separating. And now we integrate. So we integrate, and now we'll choose our appropriate limits. So what are our appropriate limits for this problem? Well, t is easy. I started at time t equals 0, and I ended at time t equals t. Then, for our q's, this capacitor started uncharged. So that was important for the setup of the problem, because you can't solve a differential equation fully unless if you know the initial condition, or at least some condition. So here, it's uncharged. So we start from no charge, and we end with charge. And now, of course, if this bothers you, putting the variable in there when we integrate, you could do something like this, where we create a sort of dummy variable, where we just call it like a primed variable. I might leave it like that for today, just to show it, because a lot of people prefer that, because it seems weird integrating and plugging in. I know the calculus teachers are mad when I don't do that. Okay, so what on earth is the antiderivative of their left side? Well, notice I have 1 over a bunch of stuff. So the antiderivative of this, you could do a u sub, but the antiderivative of this will look like natural log of this, but not quite, because we have to use the chain rule. So if the chain rule says when you take a derivative of a composite function, you got to multiply by the constant. Well, this is integration, so we have to divide by that. So dividing by 1 over, so 1 over negative RC would be just negative RC. And we're evaluating from 0 to Q. And we can already see why this is not, like, fun. And then we have just T. Integrated from 0 to T. So that side's not bad. And of course, there's more efficient ways to probably separate, but I'm not pretending you have the power of hindsight in this. So we get negative RC. And then remember that you can write subtraction of logs as a fraction. So if I plug in my upper limit, I get epsilon over r minus q over rc. And if I have my bottom limit, I would get epsilon over r minus nothing. And this is just t. So let's do some simplifying. So first, I'm going to move the negative RC to the other side by division, and then I'll simplify my log. So inside my log, notice I can distribute this epsilon over r fraction to both terms. So epsilon over r is 1, and then q over rc divided by epsilon over r. Well, the r actually cancels, so I get q over c epsilon. All right, then we will E both sides, because if E and ln touch each other, they cancel. So then I get 1 minus q over c epsilon is equal to e to the negative t over rc. And then if I add q over c epsilon to each side, I get 1 equals q over c epsilon plus e to the negative t over rc. I can subtract, and I can get q over c epsilon is equal to 1 minus e to the negative t over rc. And now we're done because we can multiply by c times epsilon. Wow, that is not fun or quick. So I'm going to show you a much better way of doing this now. So this c times epsilon, we said q is cv. So this is q max. So as expected, we do actually get like our exponential approach parent function, where there's the maximum asymptote value in front, and then 1 minus e to the negative t over time constant. Okay, so what is this better method that I've apparently been hiding? Well, this is not as weird as it sounds. So this is how most differential equations in an introductory course begin. It's you kind of have a feel of what the solution should look like, and you guess it into existence. So what does my equation look like? So it's important you have it solved for the derivative. So here I have the derivative of q with respect to time is equal to a constant minus another constant times q. Well, that looks pretty exponential-like to me, right? The derivative of e to the t would be e to the t times some constant, depending on what the exponent is. So we're literally going to make a guess that based on this like circular relationship that the derivative of the function depends on the function, we're going to guess that it looks like an exponential plus some constant. And we have to determine these scaling factors. So why can we do that? So first, we know that if it looks like the derivative of the function is the function itself times this constant must be the exponent by the chain rule. So the reason we solve it for dq dt is to show you what chain rule exponent goes in your exponential. So how can we figure out what a and b are? Well, we need two equations. So this is why we studied short and long-term behavior, right? It's always easiest to check the final case first. So we know that q at infinity is going to be the steady state charge. So what happens after a long, long time? Well, the capacitor gets fully charged. So this means we're at our maximum charge, which is c times epsilon. So if we plug in, we'd get a times e to the negative infinity plus b equals c times epsilon. E to the negative infinity is 0. So this tells us our first constant of the function is c times epsilon. And now we'll play a similar game with our short time analysis. So what is q of 0? Well, q of 0 is equal to nothing, because we're initially uncharged. So that means we can plug in and get a e to the 0 plus b, which we said was c times epsilon, is equal to 0. E to the 0 is 1, so we see a exactly needs to cancel c epsilon. So now we've determined a and b, so we get q is equal to negative c epsilon e to the negative t over rc plus c epsilon, which is equal to c epsilon times 1 minus e to the negative t over rc, which is exactly our expected solution. So I absolutely think method 2 is easier, and it is fundamentally sound. There's only one pitfall, and the pitfall here is not solving for dq dt, so you pick the wrong constant to go in your exponent. But of course, if you know it's the time constant, you don't actually need to really know that. So guessing and checking is actually really valid for differential equations, especially when you know what family they live in. So that's that. I know we went on a detour there, but I think that will be very beneficial if we learn this sort of method 2 for solving the equation. All right, now let's do it backwards. Let's do it backwards, where we have the charged capacitor, Q naught is C times epsilon, and it goes through a resistor. So we'll set it up exactly the same way. So all of our voltage drops and gains have to sum to 0. So this is important. We start with this. We gain volts across the battery. We drop volts across the resistor. We drop volts across the capacitor. And then we're back. But you're probably asking, wait, there's no battery in this circuit. You're exactly correct. There is no battery in the circuit. Get rid of it. This ensures your signs will work out. So that's why I said we have to include this battery term. You don't have to. There's some manipulation you can do. It really stems from dq/dt being the absolute value of charge change with respect to time. It's much easier just to invent this battery and cross it off because there's no battery. We said that delta V across a resistor is IR. Delta V across a capacitor is Q over C. And this is not a differential equation yet. This is not a differential equation yet, so we got to write this as negative R dq dt minus 1 over C times Q is equal to 0. So we can get dq dt will be equal to negative 1 over RC times Q. And this is actually a much easier differential equation to solve than the last one because it's just pure exponential decay. There's no like forcing term, or there's no constant term being added. This one, I think we will just do the old-fashioned way of separation of variables because it's a lot easier. So we can write this as dq over q is equal to negative 1 over RC dt, because there was just one thing to move. I just had to move the q to the other side. And then here, t is easy once again. And then for q, we start charged. So it says we start with a charge of C times epsilon, and we want another charge Q at some time later. So then, using our log rule, we're going to get ln of Q minus ln of C epsilon. So this simplifies to ln of Q over C epsilon when we do that antiderivative and plug in. And then we just get a T on the other side. So then we can E both sides. So we get Q over C epsilon is equal to E to the negative T over RC, which means that Q is equal to C epsilon E to the negative T over RC. Now, if you used method 2 on this, I feel like we don't need to go through it. It's pretty straightforward, actually. If you use method 2, it's the same idea. You just plug in your two initial conditions. So you'll still have the same guess that it's A times E to the negative T over RC plus B. You'll just see that B equals 0 when you plug in because Q of infinity is 0, fully discharged. And you'll see that A is C epsilon because Q naught is C times epsilon. Method 2 enjoyers, you can always do this. Even on the exam, you never get any points for anything other than separating and then just getting the answer. The points are basically all in the setup. All right, so here we have the first of many of these multi-switch problems, where you can have your switch in multiple states of this RC circuit. So in our first situation, it says we have an uncharged capacitor, and at t equals 0, we flip the switch over to position 1. So that's going to cause the capacitor to charge. It says we wait a long time, meaning much, much greater than RC. So that's what we mean by long time. We mean many, many RCs later. And then it says we move to position 2 for a long time. So we see that in position 1, we're going to charge up the capacitor. It's going to build, 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 and then it's constant. Then we quickly flip to position 2, and it's just a capacitor and a resistor, so it's going to discharge. So maybe let's model what's going on. So first it says graph the charge of the positive plate on the capacitor as a function of time. Well, what we should probably do is we should define ourselves an asymptote. It doesn't actually tell me to label any values here, but I think I will. You are not the dotted one. All right, so what is this going to look like? Well, we know that first, let's change this. I don't like, let's make this like blue. Because I like to make my graph red. All right, so we start uncharged. And then we know we're going to end fully charged. Because that's when this like switch gets flipped. And this is totally not a straight line. Still not straight. There we go. That's better. Still not great though. You know what? I'm done with that. Okay. So charge. Many RCs later means I hit that horizontal asymptote basically. You can assume it's basically fully charged. And then it's going to discharge. So this isn't something we could totally grade. Also, we know this is C times epsilon. Because it is fully, it's going to have the full battery potential difference when it's fully charged, because there aren't those like other resistors that it has to share with yet. It's just a single loop with the R and the C. So when it discharges, it actually connects to a different resistance. So it will have a different time constant because it goes from R to 3R. So actually tau increases. So tau is actually going to be larger when it starts to discharge. So it's actually going to discharge at a slower rate than it charged. So I might show something like this. Like it's definitely going to discharge, and maybe I'll make it a bit more like exponential, but show that it's still like not discharged yet. So we get this kind of shark fin type graph. Saw a lot of these on AP grading at some point. I feel like we saw a graph. It was supposed to be of like sine squared, and we called this guy the shark fin. But I can't grade you on this, but realize it was supposed to decay at a slower rate. I don't even know what that really means in a graph. Without a grid, you can't quantify that. Sketch a graph of the current through the ammeter as a function of time. Drive a downwards current is positive. All right, so what does that mean? So let's draw both cases. And then we're going to check for consistency. So we know we're going to have two regimes. So this is the circuit 1. So when it's in position 1, it looks like this. My capacitor kind of looks very battery-ish in that picture. There we go. All right, so circuit 1, what's going to happen? Well, we know that the current is going to flow like this. And that's going to mean that you get positively charged because conventional current flow. Because the positive end of the battery connects to the positive capacitor plate. Cool. Now, what's going on in circuit 2? Well, circuit 2, we still have this charged capacitor, except now we're discharging through a 3R resistance over here. So what is that going to look like? Well, still my charged capacitor, but now my capacitor is acting like a battery. So it is going to dump its positive charge around a loop like this. So actually the current will reverse direction through the capacitor branch after I flip the switch, because it starts with conventional current flow throwing down through the capacitor, which we defined as positive, and then it ends with conventional current flowing upwards. And of course, daily reminder, it is not actually flowing through the capacitor plates. Charges are being ripped off the negative plate, or they're being dumped to the negative plate, and it gives that conventional current model, but no charges actually cross the capacitor gap. So we get a reversal of direction here. And remember that short and long time scenarios still apply. So short time, my capacitor is like a wire, so I get a huge dump of current because the capacitor isn't resisting at all. So we know that as soon as I flip that switch, we're going to get a ton of current, and then it exponentially decays. All right. Then what happens? Well, then we flip the switch, and it discharges through the 3R resistance. So this is also a really subtle note, but actually the currents aren't the same when you flip the switch. So as soon as you start, you're only going through R, but now you're going through 3R. So actually, not only does the current flip direction, it's actually a third of its original value. So if this was epsilon over R, we only get a third of that as our initial current over here. And this also discharges at a much slower rate. Let's move you down a bit. Let's move this one down a bit just to make it a bit more readable. And of course, there's also the other time constant idea happening with this one. But so we might start with you over there, and you're like somewhere like here. It's just discharging a lot slower compared to that other one. So that is a really hard graph. Indicate whether your graphs are consistent with one another. Justify your answer. Well, we're just going to say consistent. Because if it wasn't consistent, someone probably would have pointed it out by now. Of course, that's not a great answer. Let's see why they're actually consistent. So what's the relationship here? We have a graph of I and a graph of Q. Well, we do have a relationship. We said that I is dq dt. And what is derivative on a graph? Well, that's equal to the slope. So let's check that out. So we begin with a large positive slope. Then we have a smaller positive slope, then a smaller positive slope, then a smaller positive slope, then flat positive slope, or approaching zero. Check, right? Then we start with a steep-ish negative slope, maybe not as big as it was at zero, and that also approaches zero. Yep, as expected. So yes, because we can see that I of t is the slope of q of t as expected. So there we go. Took us over an hour, but we got our first as expected of the day. And now to conclude, we will do a linearization problem with exponentials, which seems borderline impossible because we have this. This is not a power function. This is not something nice. So we'll have to transform it by logging. So if you have a discharge relationship, that's one of these that just falls, you can take the natural log of both sides to do a linearization. So the trick is to log it. Because again, we don't really curve fit in APC, we more do the linearization. So this only works if you have a discharge or decreasing relationship. If you have the exponential approach, that one, you gotta figure out a different quantity. So we'll show that this is linear. So this is a common parent function. We know the current through these objects typically decrease. So it's pretty safe to assume that most of these capacitor problems have a current function that looks like that. So let's show that that linearization trick works. So let's do it. So I is equal to I0 e to the negative t over tau. And we're saying the trick here is to ln both sides. So if I take the natural log of I, that's going to be equal to the ln of this entire quantity. So this is the first mistake. The first mistake people do is they do this. You can only cancel ln and e if they touch. So we actually have to use the power property, or sorry, product property of logs. So remember, just like you can turn products and just like you can turn subtraction into division, you can turn addition into multiplication and vice versa. So if you're trying to break apart a logarithm product, that is addition. So we can write this as ln of I0 plus ln of e to the negative t over tau. And now we can cancel because ln and e are touching each other. So we get ln I is equal to ln I0 plus negative t over tau, so minus t over tau. Let's do some rewriting. So we can write ln of I is equal to negative 1 is a constant, and the time constant, 1 over tau, is a constant. So I can write this as negative 1 over tau times t plus ln of I0. And that actually is the end of our task here, because we see that one of our variables, t, appears on that side, and our other variable, we can shove in a box as ln I. And this follows y equals mx plus b, because we get purple equals some constants times the blue box plus another constant, which is the y-intercept. So this is linear with the slope and y-intercept as our expected values. So this becomes our y, and this becomes our x. So this is the most challenging linearization we'll have in this class, is the exponential ones, because you have to know to log it to get rid of that exponential. And also, this is weird because we get a y-intercept, but we're also going to get a negative slope. Lots of weird things going on with this. So we have a 30 microfarad capacitor is discharging through a resistance we wish to calculate. So we've given the current at different times, which are in microamps, and then we want to solve for R. So we're given C is equal to 30 micro, so 30 times 10 to the minus 6 farads. And R is the thing we want to calculate. Okay, so why is this something we can do? Well, we just did all this work to show that for these capacitor functions, the discharge graph can be linearized like this. So we know that we can write ln of I is equal to negative 1 over tau times t plus ln of I0. So we can graph ln of I on our vertical axis, and we can graph t on our horizontal. This is not the only linearization you can do. You can mess with some things to make your life easier if you choose, but this is the standard one. And we like this because the time constant, which relates to R and C, is our slope, and our initial current, I0, which is not asked for right now, but it will be, is our y-intercept. Okay, let's do it. And by let's, I mean, I of course did the mining off camera and graphed it and Desmosed it, and we'll just plug in. All right, so when I say this is a weird looking graph, it's weird. So notice that my ln's were all negative numbers, and I get a negative slope, but it did fit well. And it makes sense, because natural log says what power do I have to raise e to? And if these are all 10 to the minus 6, we're going to get some pretty big negative exponents. But realize the fit was good. This was linear. If I didn't linearize it, this looks like this, right? It's some sort of exponential decay that touches the y-axis. So it's linear now. Okay. So now we get our Desmos regression, and Desmos gave us a slope and a y-intercept, which are the two things we need. So we're going to solve for a couple of things now. Calculate the time constants. Well, we said that our slope of our best fit line was -1 over the time constant. So this means that our time constant tau is just -1 over the slope, which is -1 over negative 0.0336, which is roughly 29 seconds. And again, the unit of time constant is seconds. So this means it roughly took about 29 seconds for this capacitor to halfway discharge or halfway charge, whatever we want. So how do we find R now? Well, we have an equation that says tau is equal to R times C. And we know what C was. C was 30 microfarads. So R is tau over C, which is 29, divided by 30 times 10 to the minus 6. And if we work this out, we get R is approximately 999,000 or something like that, 990,000 ohms. So R is roughly 0.99 capital M for mega ohms. So this is almost 1,000,000 ohms of resistance needed. And that should make qualitative sense because our time constant is normal seconds, right? 30 seconds-ish. So if our capacitance is millionths of a farad, our resistance must be millions of ohms to make tau multiply to a single or double digit number. And then we'll conclude by finding our initial current I0. So we also can use our y-intercept, because we said the y-intercept of our graph also had significance. It was the natural log of the initial current. So we actually said that y-intercept of our graph was ln of the initial current. So if I solve for initial current, I can E both sides, and they do cancel because E and ln touch each other. This means that I0 is equal to E to the y-intercept, and that's a really weird looking equation. So I get E to the negative 12.55. And if you plug this in, you get a whole bunch of zeros, but I got 2.5 times 10 to the minus 6 amps, which is roughly 2.5 microamps. And with that, we are finally done with our RC circuits. That is absolutely a lot of work. Oh, we can check that this microamps makes sense. I got 2.5, trying to extrapolate to get what happened at t equals 0. Yeah, I believe that. That seems reasonable. That's just a little bit more. Well, it's actually a lot more in comparison because of the exponential. So yeah, that's everything RC, from short times to long times to transient to the diffie Q and to lab stuff. No shortage of content for RC.